In this video, we will do some review of the dot product and do an example eventually towards the end where we use it in an application of work in physics. Okay, so there are a few properties of the dot product that I want to recap. Okay, so when you take the dot product of two vectors, one of the formulas that we had for this was it equals the length of u times the length of the vector v, and then times cosine of the angle in between them. So in practice, that's usually not what we use to actually compute the dot product. We do the dot product, so let's say I had 1, 2 dotted with 3, 4. We take the dot product by multiplying the corresponding entries together, so I'd multiply 1 times 3, and then you would add that to the product of the next corresponding entries. So to 2 times 4. So this will be 3 plus 8, which is 11. So usually in practice we use this formula for the dot product because it's quicker. But if we're interested in stuff like angles between vectors and whatnot, then this first property of the dot product, using the lengths and the cosine of the angle, can be useful. Okay, so one of the results of this first property is that it lets us check for when two vectors are perpendicular. So u and v, two vectors, are perpendicular if and only if, so this double-sided arrow means if and only if, their dot product equals 0. So if my vectors are perpendicular, that would mean that theta, the angle between them, would be 90 degrees, or pi over 2. And cosine of pi over 2 is 0, so my dot product would be 0. And vice versa. Okay, so this is an if and only if statement. Okay, so the other thing that I want to recap is work, the concept of work in physics, can be computed using a dot product. So work is equal to the force vector dotted with the displacement vector. So F stands for force and D stands for displacement. And we'll do an example later in this video involving work. Okay, so in that example, I'll review, for example, like what displacement is. All right, so let's do a practice problem. So this is from the final practice problems part 2, question number 5, part B, and it's a true or false question. So it says that if the length of u is equal to the length of v, then the vectors u plus v and u minus v, so those two vectors, are orthogonal. So first, I want you to pause the video for about 3 minutes to try this question on your own first. All right, so that is super important. Like I mentioned in the previous video and maybe even last time, really the most important time during these videos is this time that you take for yourself to try these problems on your own. So 4, 3, 2, 1, pause the video. Pause the video for about 3 minutes to try this. You really want to seize this time to actively try the question. Believe that the time that you spend, even if it doesn't result in you finishing the problem in this time limit that I'm giving you, is going to be helpful. One of the things that you're doing by pausing the video and trying these questions is honing your skill, honing your ability to apply concepts that you've learned to new problems like this. Because ultimately during the test, that's what I'm going to assess. I'm going to assess your ability to apply stuff that you've learned to tackle new questions. So that's why it's important to practice that skill and really utilize these pauses. All right, so let's start to talk about this together. Okay, so I'm running out of room here, so I moved up to the top of the page. So I need to check whether those two vectors are orthogonal. So to do that, we can check if, so one of the vectors is u plus v. If that vector dotted with the other vector, u minus v, check to see if that dot product is equal to 0. Okay, so let's take the dot product. So let's do the first vector, u plus v, dotted with the second vector, u minus v. Work it out and see if it gives us 0. Because if it does, they're orthogonal. But if it doesn't give us 0, they're not orthogonal. Okay, so one of the properties of the dot product that I didn't state is, if we have something like this, the dot product sort of operates kind of like a multiplication symbol. I can distribute, or I can FOIL this stuff out. So if I do that, I will get, so first if I distribute u here and then v here, we'll get u dotted with u, and then plus v dotted with u. Now I'm going to distribute them to the next term. So to the minus v, and then this one to the minus v. So if I distribute the u, we'll get minus u dot v. And if I distribute the v to that term, we'll get minus v dotted with v. Okay. So the dot product, it doesn't matter which order I take the dot product of two vectors in. So v dotted with u and u dotted with v, they're the same. So these two things, these two dot products are going to cancel because they're equal. So I just want to make a note of that. This is just continuing some review. So u dotted with v is the same thing as v dotted with u. The order that we dot product, take the dot product, doesn't matter. But what about cross products? If you take u cross v and you switch the order, the vectors will point in opposite directions. So this is negative v cross u. All right, so I'm going to put that in a little circle here. Sorry, maybe I should say oval or ellipse type thing. Okay, so what we end up getting is we get u dotted with u minus v dotted with v. So there's a connection between a vector dotted with itself and lengths. So I'm going to do a quick example on the side to help us see that connection. So let's say u was the vector 1, 2, 3. And then I take its length. So if I take its length, what I do is I square all the entries and sum them. So 1 squared plus 2 squared plus 3 squared, and then I square root that. But what I want to notice about this is, so I have the square root, but if I look at what's inside, 1 squared plus 2 squared plus 3 squared, we could get that if we were to take the dot product of u with itself. Okay, so if I were to square both sides, I would get rid of the square root, and I would just have u dotted with u. But if I were to square both sides, the left-hand side would become the length of u squared. So that's what a vector dotted with itself equals. It equals its length squared. So in the same way, v dotted with v is going to give me the length of v squared. Okay, so we have the length of u squared minus the length of v squared. But that's definitely equal to 0, since we were given that the length of u and the length of v were equal in this problem. Okay, so my dot product is 0, so thus our vectors u plus v and u minus v are orthogonal. So as a result, so was the problem saying that they should be orthogonal or should not be orthogonal? Let's go down and just check. So let's see, it was saying, oh yeah, they should be orthogonal, and that's what we got. We got that they will be orthogonal, which means this is true. Whoops, sorry, going a little bit too far there. So this is true. Let's write that better, sorry. This is, I still don't like that. Okay, this is true. Okay, that looks better. Okay. So just as an aside, I want to show you what this statement means geometrically, because it has a cool geometric meaning. Okay, so what I was given here is we have these two vectors, u and v, and they have the same length. So we have these two vectors, They might be pointing in different directions, but they have the same length. Okay, so when we look at u plus v, to add two vectors, I use the parallelogram rule. Okay, so I use the parallelogram rule. And u plus v would end up being this vector. That's u plus v. With u minus v, it has its tail at the tip, at the head of v, and then it goes like this. Its head is at the head of u. That is u minus v. If you're not sure why that is, pause the video for 1 minute to really think about this. So after you think about it for 1 minute, if you weren't sure why that's u minus v, then I would encourage you to use our resources for help, like office hours or Piazza, to ask a question about this and why that's u minus v. All right, so we were saying that u and v have the same length. So these two vectors have the same length, which means this parallelogram, so there's a special name for it, it's called a rhombus. A rhombus is a parallelogram, I guess technically I should say it's a quadrilateral, where all the sides have the same length. It just so happens that a rhombus also ends up being a parallelogram. Okay, so what we've just proved is a theorem from geometry. Okay, we just proved that the diagonals of a rhombus are perpendicular. And that's a theorem from geometry. And I think that's pretty cool. I think it's cool that we can use vectors to prove these sort of foundational results from geometry. Okay, so let's move on. Let's look at another example. So this is from the final practice problems, part 2, and it's question number 8. All right, so the problem says that Angela uses the force vector 4i to push an object along a straight line path from 0, 0, 0 to 3, negative 2, 1. Karina uses the force vector v to push an object along the same path, but in the optimal direction. So by optimal direction, i.e., I mean the direction that's parallel to the path. That's sort of the best direction that we should be pushing this in, straight along the path that it's traveling. Okay, and when she does that, she uses the same work as Angela. So the question now asks, find the vector v in the form ai plus bj plus ck. So it wants us to write it in this form. Okay, so first what I want you to do is pause the video and try this for about 3 to 4 minutes. It's likely not going to be enough time to finish the problem, but I mostly want you to think about, what are the key ideas? How do I begin? And what do I look for in the problem that sort of indicates to me that that's how I begin? So 4, 3, 2, 1, pause the video. Pause the video and try this for about 3 to 4 minutes. All right, so hopefully you've done that. Hopefully you paused the video for about 3 to 4 minutes to try this. Let's talk about it together. So one of the key things that the problem says is these two people, Angela and Karina, they use the same amount of work. So their works should be equal. So I should be able to write something like Angela's work equals Karina's work. And we reviewed at the beginning of this video how to compute work using dot products. So for Angela's work, the formula for work is you take the force vector and you dot it with the displacement vector. But since I'm going to have to do this for both people, I'm going to add some subscripts. So for Angela, I'll put A as a subscript. So Angela's force vector and Angela's displacement vector. Okay, equals, and on the other side, I'll do the same thing, but with Karina. So I'll do F subscript K dotted with D subscript K. Okay. So Angela's force vector was given to us. So Angela's force vector was 4i. This was her force vector. I'm going to write that in this bracket notation. That's 4, 0, 0. And we need to dot that with her displacement vector. So she's moving this object from the point 0, 0, 0 to the point 3, negative 2, 1. So the way I get the displacement is I take the final position minus the initial position. So I do that coordinate by coordinate. So 3 minus 0, comma, negative 2 minus 0, comma, 1 minus 0. So the point 3, negative 2, 1, that's the final point. And 0, 0, 0, that's the initial point. Okay, so on the other side, this is equal to Karina's force vector. We're calling that V. So I'll just write V here. And the problem says she's pushing the object along the same path. So she should have the same displacement vector. So if I simplify that now, it's 3, comma, negative 2, comma, 1. She's got the same displacement vector. So same displacement vectors. The problem told us that. So that's why this and this are the same. All right. So the problem tells us a key fact about this vector v that we're trying to find. It tells us that v is pointing in the optimal direction, i.e. it's parallel to the path. So v is parallel to the displacement vector, parallel to 3, comma, negative 2, comma, 1. So when two vectors are parallel, so that means v is a scalar multiple of the other vector, a scalar multiple of 3, comma, negative 2, comma, 1. Okay, so that means that, oh, whoops, sorry, that for some reason it massively shifted down there. Okay, so that means that v is equal to some scalar, I'll call it c, times the vector 3, comma, negative 2, comma, 1. So I could distribute the scalar in to get 3c, comma, negative 2c, comma, c. So the vector v needs to look like this. All right, so let's take these dot products. So on the left-hand side, I do 4 times 3, which is 12. And then I have 0 times negative 2, which is 0. And then 0 times 1, which is also 0. All right, so the left-hand side is going to be 12. On the right-hand side, I got to take the vector v, which is now written down here, and dot it with the vector 3, negative 2, 1. So 3c is going to multiply 3 to give me 9c. Negative 2c multiplies negative 2 to give me plus 4c. And then c multiplies 1, so that gives me plus c. All right, so simplify this now. So we have 12 equals 14c. And if I isolate for c, we get c equals 12 over 14. And if I divide the top and the bottom by 2, we get 6 over 7. Okay, so that's what c is. Let's remember, what did the problem want us to find? Oh, the problem said find v. Find v and put it in this form with I, j, and k. Okay, so I know what c is. Let's take our c value, and now let's plug it back in to the vector v. Okay, so thus, the vector v is going to be, so it's 3 times c for the first component. So I'll put this I hat, and then minus 2 times c, minus 2 times 6 over 7 for the j component, or the y component, and then plus, then I just plug it into c, and I just get 6 over 7 k hat. All right, so we're almost done. We could just simplify this a bit. So we get v equals, if I multiply 3 times 6 over 7, I get 18 over 7 I hat. The next term is minus 12 over 7 j hat, and then last term plus 6 over 7 k hat. And that is my force vector. So that is it for this example.